Your network doesn't operate in a vacuum. Every change you make has a direct business impact. So why make changes quietly in your silo? Orchestrate your network automations to integrate with the rest of the business using iTential. Visit itential.com to find out more. That's itential.com. Welcome to Heavy Networking, where we've got a hardware show for you today. We're going to discuss TCAM, high bandwidth memory, allocating these expensive memory resources, and why it is a complicated problem. Now, if you've ever had to select like a switching database manager template, SDM template, or done similar operations on a switch, this is your episode. I am Ethan Banks with Drew Conry Murray, and we are your gentle co-hosts who you can follow on LinkedIn, Blue Sky, and the Packet Pushers community Slack channel, and please do. Joining us for this discussion is LJ Wobker. LJ's a principal engineer at Cisco, and when I asked via LinkedIn for folks to raise their hands to discuss this complex topic of high-performance memory and network switches, he got in my DMs. We had a great conversation, which continues here today. LJ, welcome to Heavy Networking, and in a sentence or two, would you tell the nice folks who you are and what you do?
Hey, Ethan. Hey, Drew. Yeah, sure. Like you said, I'm a principal engineer at Cisco. I've been there mostly nonstop since 1997. I started when I was still in college at North Carolina State in the TAC, did that for a while. And I now kind of spend maybe half of my time in the organization that builds and designs the big packet forwarding ASICs from the Silicon One lineup, and kind of the other half of my time in the system side where we design big fast routers and switches.
Excellent. Well, okay, so let's set up this conversation because there's a lot to talk about, and I want to jump right into this thing. So let's start by seeing if you can correct my brain or confirm that I think correctly about these things.
All right.
And LJ, as I see it, the fundamental job of a switch is to take in a packet. I mean, technically, we're talking about Ethernet frames if we're assuming an Ethernet switch.
Sure.
So it's got to take in a packet on one port, figure out what port it's supposed to leave on, forward it out that port, do it as fast as possible, and it might need to transform that packet in some way before it does that. It might need to do encapsulation, encryption, MLS tag, push pop, VLAN tag, and QoS marking, etc. Okay, with that very basic explanation there, am I thinking of a switch's job correctly? And are there any nuances that would help clarify my thinking?
Sure. So you've definitely got the first order bit set correctly. I think the part of that blurb that's doing a lot of work is the might need to transform the packet and might need to figure out where to send it. So back when I was at Barefoot and P4 as a programming language had just kind of come out, the example I would always give people is the 8-port totally unmanaged, super cheap, whatever switch that everybody's got under their desk, to connect things, basically does a single lookup forward. Like, it is almost literally as simple as frame comes in, pull the destination MAC address off the frame, look that thing up in a table. The answer that you get is this goes to port X. And it is basically that simple. There's almost nothing more to it, for these $20 switches that we've got now. So it is basically that. And like, if you go and look at how the P4 language is kind of structured, is it decomposed all of packet forwarding into a really simple set of primitives, which is basically I match on something, I do a lookup, and the answer gives me some part of the puzzle that I need to forward the packet. And it can literally be everything from as simple as Ethernet frame in, destination MAC, answer B, output B, done, finished. Great. Now, on the other end of that, it can also be I've got a packet that's coming in inside some kind of tunnel that I've got to decapsulate. I got to figure out which header I'm forwarding on. I got to figure out what does the config of that interface look like, depending on where you are. Maybe you even have sub interfaces, and kind of all of that classification and lookup work has to be done based on whatever the config of the switch is. And then you have to store all of that forwarding state somewhere, and that's a lot of what we're going to talk about in the next few minutes. I got to store all that state, and then when I do all those lookups, and imagine a billion deep if then else construct for how I forward the packet. And at some point, I kind of collect all the answers that say, all right, it's going to physical port 27 and it's going to logical port 37, which means either this VLAN tag or this VXLAN header or whatever other headers it is. And now I got to figure out how much of this packet do I need to change, right? Because if you go back to our Ethernet frame example, I don't change anything in the packet, or I don't change anything in the frame, right? If like a pure straight Ethernet switch, the bytes that come in look exactly like the bytes that are going out. And so depending on how complex your forwarding chain, if you just do IP on top of that, now basically the only thing I'm changing are the source and destination Ethernet addresses, right? If you think about just forwarding an IP packet as an Ethernet device, that's really all I'm doing. But now I'm doing my lookup on the IP address, and somewhere now I got to store, I'm changing the source MAC address because now it's coming from me, the router, and I'm changing the destination MAC address because it's going off to somebody else somewhere. And so now I'm doing, I don't know, 3 or 4 lookups, and I got to store 2 or 3 pieces of state, right? And so kind of every time you add a feature or add an end cap or add any complexity in the forwarding path, I've got to figure out, how do I parse that packet? How do I figure out where it's going, like literally physically, and then figure out how am I going to manipulate the bits on the other side so that whoever's next in the track knows to expect it, and it looks like something they know how to process. So yeah,
Okay,
you've absolutely got the primitives, and it's just a matter of how deep the rabbit hole goes.
Well, so let's walk through an example then with the rabbit hole going a little deeper. So if I've got to do some kind of a transformation, what's that look like? Walk us through a frame getting switched from port to port, and assume there's some transformation along the way to help us map what's actually happening inside the switch to set up the rest of our conversation about memory here.
Sure. So, and I'll caveat a tiny little bit. One of the things you will definitely hear me say 100 times is every single piece of switching silicon that's ever been built does this in at least a slightly and often a very much different way. One of the biggest challenges for this part of the universe is all the hardware is subtly different, and nobody consistently uses the same terminology for anything. So I will try to use the more standard terms if and when they exist. But one of the things that, and I guess I'll put my hand up and say, if people want to ask questions on the Slack channel later, it's like, oh, this side of Cisco calls this thing green, and this side of Cisco calls this thing seafoam green, and some other company calls it a different shade of green, and some other case, and in reality, it's all the same thing. And so, I try to encourage people to think through the concepts, right? Like, what are we doing? If there's an RFC on it, then we probably have some terms we can agree on. If it's some implementation, then marketing people get involved and they want to call it something that they can either brand or copyright, or I'm not allowed to say bad things about the marketing people because I'm a marketing person. But there's all of that sort of stuff. So as frame comes in, and you basically, the first thing you do is you parse it. So as the thing comes in off the wire, you almost only know 2 things. What are the bytes in the frame, and where did it come from, right? The hardware basically just says, this frame showed up on port 7. And that's basically all you know, right? And so one of the first, you got to go and parse the packet, which basically says, in my universe, we guarantee that it's Ethernet, because on the box I work on, we don't support anything else. You go back to Sonnet and Serial and all sorts of stuff, but again, the physical port attributes will tell you what kind of frame you're going to get. So I know I'm going to get an Ethernet frame. Awesome. So I start parsing the packet. Destination address, source address, ether type, very important, right? Because ether type basically tells me what branch to follow in the parse tree.
Ether type being a bit in the Ethernet frame header.
Exactly. That says, either it's, most commonly it's IPv4, or it's IPv6, or it's MPLS, or it's something else, right? And so the ether type literally just says, this is the next header, so that you know what to get. If we didn't have ether type, we'd either have to make educated guesses, or you'd have to hand program. You'd have to literally say, on this port, the VLAN 174 is always going to have IPv4. And then you'd never be able to have both mixed v4 and v6 and things like that, right? So ether type basically allows you to just kind of identify whatever's next. And kind of every protocol with the exception of MPLS, never mind, has kind of an equivalent of, hey, tell me what the next thing down the track is so I can figure out how to parse it. And so in the hardware, one of the things that we have to go and build is literally the parse tree. And so if you start at the root, it says Ethernet, and then it branches to what things might I know? And almost everybody's going to know the things I said, right? V4, V6, ARP, ICMP, all of these things that have different types that are in a spec somewhere, we code them up. If you are in a resource constrained environment, which basically everything fast is to some degree, you will have some limits somewhere on how big that parser can be, right? I can't, if I've got a finite amount of memory, I cannot build a arbitrarily large parser in hardware. Now, for reasons that turns out to not be the really expensive hard part, but Wobker's 757th law of networking is if the parser is capable of holding 200 headers, someone will find the 201st. Right. That is universal, right? There is, that's always how it's going to work. So you come in, you parse the packet, which basically sets up, you can almost think of them as like setting pointers in the frame, right? And so it'll say Ethernet begins here, some number of bytes later, I'm going to make it up, IPv4 lives here, some number of bytes later, TCP lives here, and on and on and on. And like if you're trying to move IP packets really, really fast, we probably don't care about anything past that. Like we don't parse HTTP headers, at least not on the boxes I work on. But
that is the switch to forward, it only has to parse so deep into the headers, and then it doesn't care about the rest.
Right. And the complexity, like if you want to do a server load balancer, you've got to be able to get to the thing that you're load balancing, right? So like you've got to be able to get down into the TCP session layer, maybe even parse the HTTP headers, things like that. And basically everything in hardware, well, it's true everywhere, but it's really noticeable in hardware, is there's always this trade-off between performance and complexity, right? If you say, I want to parse a bunch more stuff and do a bunch more work, then you either have to create more hardware that can do it the same speed, or you have to live with it going slower. And in some cases, you just can't do it at all because the hardware just isn't designed to do it. And of course, we run into that all the time. So
just a quick question.
Yeah.
So you said, one of the first major decision points is the ether type, which gives you some information, and you sort of start running a parser to go through those ether types and figure out what to do next. Is this sort of where the device is now using some amount of memory for this process?
Yeah, the parser itself, the however it's implemented, and there's a bunch of different ways, that parser, the state of that parser has to live somewhere. Mm-hmm. And so depending on, like you're also going to hear me say, depending on the implementation about 7,000 times, only because it's true. Depending on the implementation, that parser might be its own completely unique block of hardware somewhere, where only the parser can use it. And if it fills up, you just can't parse anything else. Or sometimes it shares memory with some other blob, and then you have to worry about how do these two things interact, which is probably worth, the segue here is, the greatest part about having memory that two different applications or multiple different applications can use is that multiple different applications can use them. The worst thing about having memory that multiple applications can use is exactly the same thing, because now you have to deal with, it's like, okay, Barbara took this much memory and Bob wants this much memory, and they can't both have it at the same time. So one of the things that we do, especially as you get to the really high speed stuff, is you have to nano manage every single memory access, because that pipeline has a very, very specific budget. If you want to forward 10 billion packets a second, you've got to know where every single memory access is, exactly how big it is, exactly where it's going, so that you can pipeline the whole thing.
In the systems you're working on, has the design decision been to allocate, specific memory to the parser only, or to share it with other applications? What's sort of the common approach?
So for really high speed stuff, generally the parser is kind of its own blob. Mm-hmm. Not every single one, but that's generally how it works.
Okay.
And so then you get it parsed, and then at some point you have to go and look up what interface it came in on. So imagine you've parsed it and you figured out it's Ethernet, it's got a VLAN tag. We'll use the single tag case just because it's easier. That will basically tell me what logical interface it came in on, right? Cisco calls these sub-interfaces, depending, people use different names again. But if I've got a forwarding policy or a QoS policy or some feature configured on that interface, that's an attribute of that interface, right? Like it will say something like, I am forwarding IP packets on this interface, right? There you can say some routed ports versus switched ports. You can almost think of that as, am I looking at the IP destination address or am I looking at the Ethernet destination address? Because from just the frame, I don't know that, right?
Mhm.
I have the frame, the physical port number, because that's a hardware property. And then I got to go and do a lookup that says, okay, if it came in on this physical port with this VLAN and the ether type is purple, that means I want to go and look at the IP destination address. Or maybe somewhere in there it says
Hmm.
it's IP, but I've got a GRE or VXLAN tunnel configured, which means now I don't just have one IP address, I've got IP inside IP. And so now I look at the outer one in yet another table and say, is this IP address configured somewhere as the destination for a tunnel? And that's a table somewhere, right? And maybe it's 100 entries and maybe it's 10,000 entries, but somewhere I basically say, if this destination IP address is in this table and the answer is, hey, you're terminating a tunnel, now I've got another branch off into some other blob of the code. And so generally speaking, what we'll do is we'll kind of parse the whole thing in advance because that's not going to change, right? If it's, we might not know whether we care about that inside IPv4 header, but it's generally speaking easier to just parse the whole thing so that I've got the pointers in case I do need it. And so then, let's ignore the tunnel thing for now and say, okay, it's an IP packet. One of the other things I got to check is, do I have a QoS policy on this interface? Do I have an ACL on this interface? Am I making mirrored copies of packets that come in on these interface, right? And you can almost think of these as, you can think of them as either flags or bits, kind of depending on how you want to mentally model it. Like the flag would basically say either this feature is or is not enabled, or you can think of it as, if I support 1,000 different ACLs on the system, that's a 10-bit number, right? I need 10 bits that represent which, not just that I have an ACL, but which ACL do I now apply to this packet? And if I've got an ACL applied, now what I got to go and do is figure out what are the fields from the packet, and we generically call it metadata, right? Which is basically stuff that comes from the config that isn't in the packet header, like the port number. And if you're doing the timestamp or the traffic class, kind of all this stuff that it's incredibly relevant to how I'm going to forward the packet, but it doesn't live in the packet itself. So that's the really generic term that we use. So if I've got an ACL, now I've got to go and say, okay, which fields from the packet am I going to use for this ACL? And of course, the normal ones would be the IP source and destination, the TCP port numbers, source and destination port, maybe the type of service byte. Somewhere in there, I have to encode what the interface is, right? Because most systems don't do system global ACLs. You generally put an ACL on the port, right? So what I'm really doing is I'm building a key. And that key might be a couple hundred bits wide. It might be even wider than that. Again, it depends on what are all those fields, right? So you add up all the bits that you need. You always need one more bit than you have. So you have to fight with people over which things they get to support. And you do all of that sort of stuff. And what you basically end up with is a lookup key. And it might literally be something like the source and destination addresses, the source and destination ports, the type of service byte, the time to live of the packet, the size of the packet, what logical interface it came in on, maybe what logical interface it's going out of if you already know that, although sometimes you haven't figured that out yet. And that basically just becomes a lookup key. And you throw that lookup key at some other table. Ding, ding, ding. We'll talk about TCAMs. And you get an answer. And if it's purely a security ACL, you can almost think of the answer as just being drop or forward. But sadly, for us poor hardware people, most people don't just want drop or forward. They usually want drop, forward, and count. And so if I've got to count it, now I've got to figure out, I'm basically building another key to go and punch the counter memory. Because if you want me to be able to deliver counters like per port, so that you, like, if I say, you could say, if I drop the packet, punch counter, No problem. Now I need 2 counters, one for all the packets that passed and one for all the packets that dropped. But if what you want is, I want to know that you dropped it, and I want to know what port you dropped it from, now I've got to have one of those counters per port. So, okay, no problem, just more memory. And if I want to have counters per port and per entry in the ACL, now I got to have a lot more counters, because if that ACL has got 1,000 lines in it and I've got 100 ports on the system, and in theory I can do that everywhere, the number space is starting to get pretty big. And especially when you get to these like really heavy service aggregation platforms where you've got literally thousands of logical interfaces on the box, you cross thousands of logical interfaces with thousands of entries with directions and counters, and you start dealing with some pretty big number spaces. So then you eventually figure out, where it came from, if you're going to do things like an ACL or what other features you're going to do. And then at some point, you got to figure out where the thing is actually going to go. And so if it's a layer 3 lookup, everybody has some implementation dependent version of how they build their fib, right? Fib is a sort of generic term, although not everyone agrees on that either. I guess
fib, forwarding information based,
forwarding
the table
information
that
based.
is once all the routing protocols and everybody's weighed
Correct.
in. This is what has been populated as the way I'm going to forward traffic through this switch.
Yep. And so you can almost think of it as, if you go way back in time, back in the 90s, we basically forwarded things based on what was in the routing table. That was it. We didn't do anything else.
Yeah.
And then we built what Cisco called it Ceph. It was what we call the software fib, which was a kind of a compressed, condensed, faster version of that. Probably my favorite code comment of all time at Cisco was literally in ipfib.c. And somewhere in the routine that actually did the heavy lifting, there was a code comment that said something like, "This routine is performance critical. You can and will be terminated for degrading the performance of this routine." And I was like, I was 21 years old or whatever, and I was like, damn, I am in the right place. This is awesome. I was like, these people are not kidding around. My guess is you couldn't get that comment checked into the code base today, although I don't know, maybe you could. So anyway, so you if you're doing an IP lookup, you figure out like where is it going, right? And so generally you've got 1,000 different ways to build the hardware around that. Certainly talk about that memory in a while. And so you figure out, okay, I need this thing. The next hop for this packet is 4.5.6.7. Great. So the problem is that used to be what you needed to know where to send it, right? But now 4.5.6.7 might be like an inter AS BGP next hop where you've got 5 different ways to get out of the autonomous system. And so now what I've got to do is figure out that the term we use is, load balance resolution or forwarding resolution. It usually has the word resolution in it. And so now I've got to take that kind of abstracted recursive next hop, and I've got to figure out which physical port is this thing actually going to go out of.
This is an ECMP problem specifically?
It could be. That's one of them. So imagine you've got 2 different exit points from the autonomous system. I got to figure out which one to pick. Fine, one more lookup. Now, once I figure out, I'm going out the right side, now I go and figure out, well, how many MPLS-TE tunnels do I have to get from here to there? Okay, well, I go and look that up. Okay, I've got 6. Great. Do ECMP, or maybe even not equal ECMP if you've got such fanciness going around. And you say, okay, it's tunnel 3. Great. All right, now I've got tunnel 3. Well, how many different ways, like what's the actual next hop for tunnel 3? Oh, sweet. Damn it, it's a link bundle. Okay, here we go again, right? It's an 8-member link bundle.
Yeah.
So now, like what if, and think of it as this big fan out tree that I'm just walking back up. Right? It's like I got to get to this way. There's more than one way to do it, and then there's more than one way to do that. And at least in theory, these things can be arbitrarily deep. In reality, they're about 3 or 4 in almost all the somewhat normal use cases. And so eventually, you say this thing is going out bundle 7, which is tunnel 12, which goes to exit point 3. And what I really care about is that is going to go out physical interface 0x123 green, which a mortal human would call 400 gigabit 0/1/2/3, right? And so now I've got the actual thing, the actual place it's going, right? Now I know where I'm actually going to write the bytes, but I don't yet know which bytes I'm going to write, because I've got to go and manipulate all those headers that might have changed, right? If it's coming off of a host and I'm stuffing it into one of these complex tunnels, now I've got to figure out what's the VXLAN tunnel ID, or what's the MPLS-TE tunnel ID, or the segment router header, or pick whatever your favorite encapsulation drink of choice is. And so as I've walked that resolution tree, basically every time I do a lookup and get an answer, I basically get kind of the, here's the next thing in the chain that you need to go and look up, right? And I also get usually a pointer, sometimes the actual value of what is the encapsulation that applies to that, right? So if it's a VXLAN tunnel, I'm going to get an IP address, or I'm going to get a pointer to an IP address. And for anything fast, it's almost always a pointer, because I don't want to carry around a 32-bit IPv4 destination if I can carry around a 10-bit pointer to it. I know that sounds a little ridiculous on its face. It's like, what's 20 bits? Who are we kidding here? But all those 20 bits somewhere inside the chip have to be 20 more wires. And they've got to be 20 more wires through every single stage in the pipeline. And when you do that for 5 or 6 different end caps, like, it starts to add up. And it adds up enough that, what I then get through is, when I get to the far side, so to speak, now I've got this frame's going to go to physical interface 7, and you need to put a source MAC address, a destination MAC address. You probably need to swap some VLAN tags. You got to put either a VXLAN tunnel or an MPLS tunnel, and all of those unique values live in tables somewhere, right? I've literally got a table somewhere, because what I do not want to do is carry, I don't want to carry this 12-byte source and destination MAC address. That's a lot. Like, I know it sounds crazy if you don't live in the hardware world, but like, every bit is sacred. So instead of that, I just carry a pointer to it, right? If I've got, let's make it up, if I've got 128 possible source ports on the switch, I only need a 7-bit pointer for the MAC address, for the source MAC address. It can only come from 128 places. So what I end up with is a table that's 128 deep, and the width is however many bytes are in the address that I'm going to add to the packet. And you just do that again and again and again and again, and every time you do it, you're saving some what becomes significant number of bits that you don't have to carry all the way through the pipeline. And kind of like, where we store all of that state is what makes doing really fast packet forwarding hard and complex. Like, this is, it's not incredibly complex stuff, right? Like, if you read the P4 book and you could program a little bit in Python and you didn't really care how fast it went, like, almost everybody can build a switch, right? It's not super hard to parse a packet. You just go and find the RFC, and it tells you what all the values are that you care about, and you just code them up and build an array, and off you go. But when you have to do it super, super fast in hardware, you're literally, I always joke and use the term, you're nano managing all of those tables. Like, they've all got to fit somewhere. And on one of the chips that I work on all the time now that's shipping, it's a 20 terabit chip. It'll do about 10 billion packets a second. And each of those packets is something like 40 like memory accesses in like what we call the big databases, the big tables, and another 20 or 30 memory accesses in the like little teeny tiny memories that are inside the chip, or that are like in the forwarding engine guts of the chip. So you're talking about call it a 500 billion memory accesses a second. It's something like that. It's a bonkers number. And every single one of them has to be in the right order at the right time. And like, you can never wait. Like, there is no, I tell people, I'm like, there's no virtual memory. There's no stalling the pipeline. Like, you're not allowed to do that. Like, the next train is coming, and you have a very, very finite amount of time to figure out where this one's going.
So is there some software running on top of all of this memory that's managing all of these lookups and where things should be and all of that? Like, an OS
you better believe it.
Yeah. Okay.
You better believe it. And so, to give you a very, very, very like an order of magnitude, idea, and one of the jokes I tell people all the time is, what you thought was a hardware problem is really a software problem. And that's not really to cast aspersion on my good software friends, but it's more of, if you think of the like orders of magnitude of how much work gets done, like how many people are working on the silicon versus how many people are working on the software interface between the chip and the operating system, and how many people are working on just the bottom part of the operating system where I program and manage all of those tables. It's really, really top heavy. There are way more people doing the work inside the operating system and doing the work in that software. We call it the SDK. People have different names for it. That glue code, some people call it the driver. That code that lives between because at some point the hardware is blindingly simple, right? It's just bits and transistors. It just does what it's told. Right? It's like I've got a hardware database that I call the LPM, longest prefix match, because what we use it for is taking a destination IP address and getting an answer. The hardware neither knows nor cares, right? It just moves bits around and program and does memory lookups and eventually gets to an answer and sends the answer back. But somebody's got to keep all that stuff straight. And that somebody is the network operating system, and it flows through the chip driver to get there.
So we have mentioned TCAM. We've been sort of teasing it. Can we get into TCAM, HBM, SRAM? What are they? Why are they so special and expensive? Why are we using these instead of like the RAM that's powering my son's gaming rig, which has a lot of RAM and is pretty fast?
And is pretty fast. And one of the things that I think is a lot of people just don't sort of follow is the relative differences between how fast some of this stuff goes. Because like the memory in a modern gaming rig is extraordinarily fast. However, it is orders of magnitude too slow for me to use in a tens of terabit ASIC. Like it can be both at the same time. And so
it's slower because it's bus constrained. The memory chips themselves are too slow. How do we mean too slow?
Yes, and some other yeses. It is so there's So if you, and I'll kind of start from there because it makes perfect sense. So the sticks of memory that everybody puts in their laptop and their PCs and in lots and lots and lots of other places and servers, that's just stock DDR DRAM. Right, DDR is double data rate, which literally means I do 2 transactions per nominal clock. Dynamic is just the way that the memory is physically built. DRAM is, and I'm gonna put my hand up and say I have a computer science degree, but I really did networking. I took one electrical engineering course and I was like, wow, this is really hard. I don't want to do that. So I'm about to talk about like transistors and capacitors as someone who doesn't actually know how they work. But I do sort of know how we use them and how the trade-offs work. So DRAM is basically one transistor and one capacitor for every bit. And if the capacitor is full, it's a 1. If the capacitor is empty, it's a 0. And the D in DRAM is dynamic. And the reason it works the way it does is periodically you have to come back and refresh it and say, hey, if this thing is a 1, I got to give it just a little more charge so that it stays a 1. And so that basic construction of memory has been around since the 50s, like the very, very, very original. If you're into a weird historical thing, go look up iron core memory, where they literally had loops of iron around crossing wires, and that's where you stored the charge. DRAM is basically that, millions of times smaller. And so DRAM is fabricated kind of on its own process. In large part because it's more efficient to customize the actual lithography process around DRAM because the volumes are absolutely astronomical. Like I could not tell you how many exada bits of DRAM get manufactured in a year, but it is a really big F number. And so there's this entire gigantic business ecosystem around just building DRAM, and there's a bunch of different specifications, and it talks about the bus widths and the clock rates and all that sort of stuff. And it's like super well defined, and those specifications coupled with the size of the market, like it is literally a commodity. There are like business analysts who track DRAM commodity prices like it's wheat or cotton. And there's whole businesses around that sort of stuff. In my universe, DRAM is big and cheap and slow. And so if I don't need to go really super fast, I'm just going to use DRAM because it's cheap and easy. So that's kind of like the bottom layer, if you will. Then the other one that we'll talk about a lot is SRAM. That stands for static RAM. And the S in static means you don't have to constantly come back and refresh it, which for networking performance thing is really neither here nor there. It kind of doesn't matter. An SRAM bit is typically fabricated in the same process node that we use for digital logic. That becomes important with how I package it on the chip. And each SRAM bit is built from a blob of 6 transistors. And if you go to Wikipedia and look up static RAM, you'll get the schematics. And maybe there are people who are listening to this who actually know what those schematics mean. I don't know. I just know it's 6 transistors. But what I really care about is it's about, and I'm going to do some hand wavy here. It's somewhere between 2 and 3 times the size per bit of actual memory compared to DRAM. And the control logic that you have to wrap around it to make it work the way we want to make it work is also about 2 or 3 times the size of DRAM. So if I wanted to do a gigabyte of DRAM, which is a totally reasonable number, like I build boards that have that much DRAM on it. The problem is that if it were even physically possible, which it's kind of not, if I needed to do that much in SRAM, it would be something like 5 to 10 times the space. It's just a gigantic, incredibly painful exchange rate. In practice, sometimes in literal physical terms and virtually always in practical terms, I never have enough room inside a chip to put that much SRAM. Like we measure DRAM usually in gigabytes, sometimes mega, usually giga, sometimes even tens of gigabytes. A gigantic packet buffer on a really fast switching chip would be like 100 or 200 megabytes. Like that is a big number for an SRAM buffer. That's all. Like if I go and tell the chip designer, hey man, you got to build me with something that's got a gigabyte of SRAM because reasons, they're going to go, I got bad news. Sorry. Like this is not a like today. This isn't even a money problem. This is just a can't be done problem. And so you get this tension between like performance and size that you've somehow got to resolve. And the building blocks for those are kind of SRAM and DRAM.
A quick sponsor message from the network orchestration folks at iTential. Automating network configuration change is a major milestone for a NetOps team. Well, what is next? Orchestrating the entire workflow. Because network changes don't begin when you kick off a script. Network changes begin with a business process, such as a ticket coming in, and then you have a change to meet the needs of that ticket proposed. Testing is then performed to make sure the change will do the right things, and then a human approves, and the change is performed, and post-deployment testing is done, and notifications are sent out, and the ticket is updated, and your process no doubt varies, right? But you get the idea. Now, what if you could take that entire workflow and orchestrate it so that your manual interaction with the ticketing system and with ServiceNow and so on, if that's all handled by an automated workflow that you designed to work with the specific needs of your shop, that would make you more efficient, right? It would increase the likelihood of not only the change getting done, but the entire business workflow being completed without error. With iTential, you can create exactly that platform. You get a complete set of tooling that gives you all the power you could need to have your company's IT and business platforms interacting smoothly. When your network operations are ready to evolve to robust orchestration of your network changes, iTential should be on your short list of platforms to evaluate. To find out more about iTential's products and how they help you orchestrate network automation workflows, visit iTential.com. That's iTential.com, and tell them Packet Pushers sent you.
Question about SRAM. You explained some of the trade-offs, but you mentioned along the way one of its main characteristics is I don't have to keep refreshing it with power. Does that mean it is like NVRAM, or what I think of as NVRAM?
No, it's really not. It's it still has to have power. It'll drain. And for the net, we could do a whole other podcast with somebody who actually knew memory and probably get into that. But from a using it in networking applications, that part's not terribly relevant. What matters what matters most to us is it's much faster. Like it is faster both in terms of the amount of data I can get to and from it, and how long it takes me to get the answer. Which is, there's kind of like these two dimensions of memory performance. There's a bunch, but the two that I often care most about are bandwidth, like how many bits per second can I cram down the channel, and latency. If I ask it a question, how long does it take me to get the answer?
So SRAM does have some use cases in the networking context. Okay.
Oh yeah, absolutely. Almost. And so if you look at the chip itself, and inside the chip, there's going to be a whole bunch of SRAM, some of which is structured into like the big databases that we think of, the NCAP tables and the LPM and all that sort of stuff. Some of it does like housekeeping stuff. We build counters out of SRAM because I need to be able to punch the counters multiple times every packet because I'm counting a whole bunch of things per packet. So I use high performance ASICs for networking, use lots and lots and lots of different sizes and shapes for SRAM. One of the really useful properties is when you design the chip, you basically have a compiler, and you can say to the compiler, hey, I want an SRAM, and I want it to be 2,000 entries deep, and I want it to be 46 bits wide. And the compiler will literally spit out the physical hardware design for that. And that's now a little Tetris block that the chip designer can move around and figure out where they want it to live. And so, whereas with DRAM, generally speaking, the sizes are really standardized, the interface widths are really standardized. You can kind of order off a pretty limited menu. With SRAM, with a couple of, with some reasonable bounding cases, I can basically build it whatever dimensions I want. So, if I want to make it twice as wide and half as deep, it's going to take more or less the same amount of space. Whereas with DDR, it's like, nope, this is how wide it is. You don't have to use it all, or sometimes you can't use it all, which makes it less efficient. So like in the Silicon One chips where I work, we've got 20, 30, 40 databases that we hit for any given packet. And each one of those databases might be a different width, right? The answer I'm storing, because if I know for sure that I'm storing an MPLS label, it's only X bits wide. Right, so I can optimize the memory and say it's going to store. If I know I'm going to store a MAC address, a source MAC address, 48 bits. There you go. Right, doesn't need to be 49, and if it's 47, it's not going to work. Right, and so you get into how much flexibility can you build into the system, because it's often nice to be able to use databases for different things depending on different packet types, that sort of stuff. But of course, all that complexity comes with some amount of cost, because you might not always fully utilize it, and the software stack that lives on top of you has to manage all of that complexity too.
All right, so we've got SRAM, which feels like it's got some special use cases. It's not the main thing that most of us are familiar with for whatever we understand about network switch architecture. There are two other memory types that we got to get into, LJ, of course, TCAM, which we've mentioned, and then HBM, high bandwidth memory, I believe that stands for. So talk about whichever one we should next in your mind.
So a TCAM stands for ternary content addressable memory, which is this big fancy long word that means exactly what it says. The content addressable part, so the way a DRAM and an SRAM work is you basically go to the memory controller and you say, go give me the value in row 7, or go give me the value in row 36. And if you're an SRAM, that row is whatever wide it is. If you're a DRAM, that row is whatever wide it was that you picked from the menu when you bought the part from somebody. And so, you kind of get the answer back. But in order to know where to look, you have to do a lookup somewhere, right? You have to say, you do some amount of logic and say, oh, okay, I want the answer that is stored in row 30 of this SRAM. That's fine. If you have something called a content addressable memory, you basically collapse that lookup. If anybody programs, think of it like an associative array versus just an array. Like if you're in Python, a list you index, a list you go get the index from. A dictionary you go get the key from, right? You give it the key and it just gives you the value. And now, so what a TCAM what a CAM does is basically it's just a bunch of hardware, which is some SRAM at the back and some logic at the front and some additional bits in the middle that let you turn that lookup key into the actual value that you want to go get. It basically just saves you a step. And so going all the way back to the mid to late 90s, we used either binary CAMs, if you want to use that term, it's not super common, or just like regular CAMs. It was perfect for Ethernet MAC addresses because Ethernet MAC addresses are incredibly long, like they're a lot of bits, and they're super sparse, right? They're not sequential. You don't. It's really, really hard to predict what any value. Like if you're doing IP addressing inside a university, an awful lot of those bits are never going to change because they all come out of the same subnets. For Ethernet MAC addresses, it doesn't really look like that. So to do kind of the first generation of high-speed Ethernet switching, CAMs were perfect. You could say the key I care about is the destination MAC address, and instead of having to build some weird table in memory somewhere to do that lookup, you just compressed all of that functionality into a hardware block and said, I'm going to give you the content and you're going to figure out the address and return to me the answer. And you do it all in hardware and it's all parallel and pipelined, and you can very, very tightly bound how long that's going to take. And so that was kind of the original CAM, and we used them in Ethernet switches forever. To be completely honest, we still use them in places. And so that's like either a binary CAM or just a CAM. The T is ternary, which is a fancy word for three, and it basically means that instead of having like just the value that you're looking for, I now have the value and a mask. And so I can basically say, I want you to go instead of saying where is 1.2.3.4, which you could do in a regular CAM, you say, where is 1.star.3.4? Where that second byte, I don't care. I just masked it off, right? Go find me anything that matches this. And so that
everything or anything?
It depends on exactly how you configure it. Super, super good question. Because the way the memory actually works is you find everything that matches that. And so when you build a TCAM, you basically have all of these rows. Like if you get out a really good microscope and you look at a TCAM, you've got a whole bunch of rows that have some value bits and some mask bits, and then an answer, which is really a pointer to an SRAM. Like you literally, it's the index for the SRAM. And so you would say, 1.star.3.4. If you looked at the mask, the second byte's worth of bits would all be 1 in the mask part. And in the value, maybe you program them, maybe you don't, it doesn't matter because they're all going to get masked anyway. And so what TCAMs let us do for networking, and the canonical use case is an ACL because it's really easy for people to kind of get their brains around, right? I can say, if it goes from this subnet to 1.2.3.4, I don't care what the source TCP port was, but the destination TCP port is 80. Like that is like the perfectly, it's super easy to think about, okay, which bits would I set and which bits would I mask to be able to filter on that format. And so that's super awesome. Then again, back to the kind of the driver and the operating system have to figure all that stuff out, right? They have to know how wide is the TCAM, what order are the fields in, where do I get the fields from, and you build all that and compile it and eventually, shove it down the channel to the actual hardware. And then when you want to match on it, the way the TCAM actually works is you've got all of these rows in the TCAM that have basically every possible rule set, I'll use that term somewhat generically, for what am I looking up? Like, does the packet match this particular line or row in the TCAM? And one of the really awesome and really terrible properties of a TCAM is it lights the whole thing at the same time. It is a gigantic parallel hardware lookup machine. So if I've got 1,000 entries in the TCAM, and the key comes in, right? Which I've built the key from all the fields that I want to check. What I am basically saying is, hey, block of hardware, in parallel, I want you to do this check 1,000 times, and I want you to tell me how many of them hit and how many of, sorry, I want you to send me a bit vector of which ones hit and which ones did not. And so I can imagine that I can encode, again, ACLs are the simple case because it's pretty easy to think about. Like I've got 1,000 ACL entries, each of which becomes a line in the TCAM. And at the far end, the hardware basically says this key did or did not match these 1,000 entries. And what I get out of that is a 1,000 long bit vector, where it's either 0 or 1. And then
and the answer comes back to you, just trying to get to the point of why we care about TCAM and why it's so critical to operations here. It does all of that work. You said in parallel, which to me means something like within a single clock cycle or within a single operation.
Yeah,
something like that.
It basically looks like one blob. Now it takes longer than one clock cycle, but it always takes the same amount of time, which means I can start a new lookup every clock. But the important thing is that it's finite, it's consistent, and it's bounded. Like I know exactly how long it's going to take, and I'm always going to get an answer. Right? The answer might be that it hit the default entry, but I'm going to get an answer. And then when I get the answer, I go to this other little memory on the side, and that tells me, hey, drop this packet. Hey, count this packet. Hey, this packet is QoS traffic class chartreuse, whatever. Right? And so being able to have this incredibly flexible hardware matching engine has all sorts of super useful applications in networking.
Yep. Okay, so TCAM is awesome. Yep. I'm using it for all of these things because its behavior matches so well what I'm doing within network operations as I forward that packet through the switch. Why don't I have terabytes of it sitting there available to me?
Because it's way more expensive even than SRAM. It's super expensive, and not just like it's substantially more transistors per bit than even SRAM. And that used to kind of be the only problem, so to speak. In really high speed stuff now, the power is almost as big of a problem as the space. Because remember where we talked about it lights all of those transistors in parallel at the same time. And so like we are now at the point where I can physically build a TCAM in the modern process nodes that's big enough that I would melt the chip. Like I get like the packaging technology does not exist. At some point, I can just make the thing bigger and bigger and bigger and bigger. And because I'm lighting it all in parallel, it generates enough heat that it'll melt itself. And so I have to constrain the size of the TCAMs and or spread them out so literally the physics people can solve the heat problem. So if the little history lesson is, I talk about like the board that I worked on that was probably the most impactful for my entire career was called Engine 5 on the GSR. And, part of the reason it was so unbelievably successful is the whole forwarding infrastructure was basically built around 3 giant 1 million entry TCAMs. And this is in like 2003 or 2004, where 1 million entries was an astronomical number, right? And it was this giant TCAM that implemented the fib, another giant TCAM that implemented the QoS and a bunch of the other features, and another giant TCAM that implemented the NetFlow stuff. And when people are like, why don't you just do that now? And I'm like, well, because we sold that board for $1,000 a gigabit. So if there's anybody out there listening who would like to pay me $1,000 a gigabit, I would be very, very, very happy, to be able to do that. And actually, I think it was more like $10,000 a gigabit back then, but it was a really, really, really big number. And so ultimately, the cost is just, it's just cost prohibitive to build the whole thing. The airline metaphor is, why doesn't everybody fly up front? What's better in every single possible dimension except cost?
And the cost is not that there's just, less of these chips being developed, so it's more expensive to make. It's actually like a physical limitation because of the energy needed to,
It's just physically bigger. Yeah. And it's at some point when you look at the cost of a chip, like to manufacture, there's kind of like the design cost. That's like human capital that goes into thinking about it and designing it. And then there's basically how big is the chip? And the bigger the chip, the more it costs. And that's not a linear relationship. That's a whole other podcast. It'd be fun to do. But when you get to really, really big chips, like making them 5% bigger increases the cost by a lot more than 5%. So you have to pay a lot of attention to, using the right tool for the job and trying to keep this thing A, to where you can literally build it, and B, to where you can build it for some price that somebody's willing to pay.
Before we talk about HBM, I want to understand something about TCAM and how the ASIC communicates with it. If we think about DRAM and traditional PC architecture, let's say, there's a bus involved to arbitrate that communication. What is there a bus between an ASIC and TCAM?
Yeah, there's always something between the digital logic, being really generic, and the memory. Again, no real common name for this. We call them interfaces. So like in the Silicon One universe, if you dig through those documents, it's going to say, and this engine has an interface number 0 and an interface number 1 to this blob of TCAM. And that interface, you basically write the key onto the interface, and some number of clocks later, you get the result back on that same interface. And so,
is that interface a bottleneck of some kind, or could it be?
It is designed. It's only a bottleneck if you want one more bit than the interface is wide. So, it is either not in the critical path because it's been designed out, or it is the only critical path because you need one more bit than you have. Yeah. So basically, every clock you can think of a lookup request goes down the interface and a result comes back. And so that the whole thing is basically built as it's not atomic, but you can think of it as like an atomic operation. It's like look up, go out, result come back. Everything happens in finite time, and so I can engineer around the variability there. Yeah.
Okay. There's no buffering. There's none of that we gotta be concerned about.
Yeah, exactly.
Wow.
Yeah. There's a rate, and that's actually a great way to put it. The TCAM is designed to do some access rate. I can do X number of lookups per second, usually a multiple of the clock frequency. And so if I'm clocked at a gigahertz, and maybe I can do 1 billion lookups per second at TCAM, maybe I can do half that. If I got a bunch of parallel TCAMs, I can multiply that number out, that sort of stuff. And that all goes into kind of scoping how much performance do you need for the pipeline.
Okay. We talked about DRAM, SRAM, TCAM. Are we ready to talk about HBM now?
Sure. HBM is actually super easy. HBM is vertically stacked DRAM that is really, really wide and really, really dense. And so, whereas normal DRAM channels are like 32 or 64-bit channels, the HBM that most folks use in stuff today is 1,000 bits wide, literally. So it's like 1,000 wires between the chip and the memory. And so the good news is that when I multiply 1,000 by big numbers of clock frequencies, I get a lot of bandwidth. That's where the high bandwidth literally comes from. The bad news is that what server and GPU people think is high bandwidth is not what networking people think is high bandwidth. And so like HBM bandwidths are, on the orders of a couple of terabits. And because of the way it works, there's like all kinds of tip and tacks that you sort of have to, it's like when we do this, we're like, oh, so take this headline number.
Wait, back up. You said the terabits of width?
Terabits of functional bandwidth per second. It's not trillions of bits wide, but it's like you've got roughly a gigahertz at the clock, and the bus is 1,000 bits wide, so that's a terabit. It's DDR, so you double, and then you do some tip tacks. It's on the order of a terabit or two of raw memory bandwidth, which is two things at the same time, right? That is a lot of memory bandwidth. But if I'm trying to do a 50 terabit chip, by the time I divide 50 by 2, I don't have room to put down 25 HBM devices, because that's what it would basically take to buffer 50 terabits, right? I just don't this is a physics problem. It's if somebody said, I'll give you $6 billion to build this thing. Oh, okay, now I'll think about it. I could do something, but it would be the whole board. And nobody's ever tried to cool it, and how would you lay it out? I mean, there's just all sorts of practical problems that don't make any sense. And so what we end up with is this kind of combo of like faster memory on the chip to handle most of it, and this like I joke, I'm like, the really slow thing called high bandwidth memory, and people are like, what? I'm like, it's just relative, right? It's just orders of magnitude different.
Is it cheaper? Because you said DRAM is the base of it. So it sounds like there's
Sure.
DRAM chips involved, which we said earlier was cheaper. So is HBM cheaper versus TCAM?
It's way cheaper per bit than TCAM. So if you plot them on a per bit cost curve, DRAM is the cheapest, then HBM, then SRAM, then TCAM. But HBM is not fast enough in any way, shape, or form for me to use in really high speed networking devices. It's like orders of magnitude too slow. It's not a little too slow, it's a lot too slow.
So despite the width, HBM does not take the place of TCAM.
Correct.
So
Absolutely not.
It sounds like. So it plays what role does it play
so
then?
Depending on where we on the Silicon One platforms, we use it for buffering some of the packets because it's super deep. It's great at that, right? It's like I can get gigabytes and gigabytes of memory in a reasonable amount of space and power and stuff like that. We can use it to offload some of the really big data structures because again, it's big. Like in the networking context, I can almost think of HBM as infinitely free space. Like in my world, I care about megabytes, and this HBM device over here is like 8 gigs. So I'm like, yeah. The problem is I can't hit it 10 billion times a second. I can hit it like a tiny fraction of that.
Used it as a, but then for an application like buffering, I don't need to do that anyway.
Right. And for buffering, I can pretty tightly constrain what that rate's going to be. And then I basically just have to figure out what fraction of these things do I have to be able to do in the on-chip buffer. That's the term you'll see in a lot of these chips. Like there's the on-chip buffer, which is the really fast buffer measured in tens to low hundreds of megabytes that live on the chip. And then there's this high bandwidth memory that in that context is super slow that has to live off to the side. And so what I end up doing is I have to try and figure out, I want to store the stuff out here, but not too much because I can't cram it all down that channel. And so you get into all sorts of, there's PhDs worth of design logic that went into managing that. And so then, and some of it is, when you look at, like, as the GPU explosion has occurred, they are dying for memory bandwidth. Like that's what limits an awful lot of what happens in the AI universe is just memory bandwidth. So when that blew up, everybody in HBM land said, we're going to go and make this faster. And I'm like, sweet, because I am happy to get on that train. Like the faster, like memory bandwidth is one of my biggest challenges. It's like, I can't physically stack up 7,000 parallel SRAMs because I just can't make them fit. And so I got to figure out some other combination, and you end up having to make some trade-off, right? It's like I cannot build you a 50 terabit deep buffered system in 2025 because the physics don't allow it. The technology simply doesn't exist. Give me a few years, maybe, but I got to figure out some other way to do it.
This has got to be getting harder as Ethernet speeds crank up, right? 800 gig commonly now, 1.6 terabits per second is on the horizon. This problem dealing with memory has got to be getting harder as we go.
Yeah, you're 100% right. And the way, there are all sorts of theoretical games, some of which we play, some of which we found out are not as effective as we thought. To some degree, you can stack up a bunch of parallel, SRAMs inside a chip. And when you stack them up or when you parallelize them, you're multiplying the bandwidth, right? If I've got 10 banks of memory, I've got 10x the clock in bandwidth, so I can scale that up. But that takes space and that takes power, and space and power are the opportunity costs of a chip, right? And so, balancing the memory requirements of what I'm trying to do and still have enough, because I've still got to also keep enough memory around to do the lookups. Right, the buffer's really
somehow you got to package this
right.
onto a line card that is 1 RU high by 19 inches wide, or whatever the actual width would be.
And never mind,
so you can slide it into a chassis and manage heat and give it enough power, and so on.
And I got to keep the thing cool. I actually did the,
let alone the optics in the front and
I
all
actually
the
did the
rest.
math the other day. The heat flux on a modern networking chip is like 25 times higher than a 120 watt incandescent light bulb.
Wow.
Like think about how
Jeez.
hot a 120 watt incandescent light bulb is. And like how close you're willing to put your finger before you like you're not, I'm not touching it. But like how close are you willing to get before it really starts to get uncomfortable? And the heat flux coming off these modern chips is like 20 times that. It's crazy. But yeah, I mean if memory were free, I'd just do everything in a TCAM, probably. Because it's just like it's better. The challenge is it's not free, and then I have to manage it and keep track of it and make sure people don't run out of it.
Well, so now let's apply all these different types of memory into where they actually show up in the switch.
Sure.
If we could, we'd use the fastest memory everywhere. Perhaps we've established we can't. But so lay out how these actually show up, and then we're going to close with the question that started all this that came up in the Slack group. And yeah, but let's start there. How do I use these different types of memory in a switch typically?
And I think so. We've sort of hit on it a couple of times along the way. So where you need the absolute ultra fastest thing, we actually don't even we use something that's even faster than SRAMs. We call them registers or flops, and that's like kilobits. And so if I imagine I need to map the DSCP value to a queue, so I'm basically taking 64 values and mapping them to 8. Right? Like I build a little teeny tiny lookup table out of pure registers and I shove it in the engine and it doesn't get used for anything else and I can never run out of it. And the software has to program it, but nobody knows it's there because nobody else can use it. And since nobody else can use it, I never run out. For if I want to look up the MAC address, or if I want to look up an MPLS label, or if I need to look up an encapsulation value, like these things, we use SRAMs of different sizes and shapes for those. There's a lot of variance from chip to chip on how big these tables are, but generally speaking, you're talking about from like a few thousand entries to a few 100,000 entries. Like there, I mean, that's pretty wide range, but that's you can build things that are that size and shape. Those are generally SRAMs because I need really high lookup rates, right? I got to do dozens of lookups per packet. They've got to be super predictable, right? I got to know exactly how long that answer is going to take to come back. So SRAMs are perfect for that sort of thing. I use TCAMs in places where the state that I'm storing really, really, really likes to be maskable. Like ACLs, again, I keep coming back to it, but it's just such a perfect canonical example, right? Building an ACL rule with something where I can set mask bits makes life so much easier. Then one of the most complicated databases in the system when you're trying to go fast ends up being the LPM or the hardware fib, right? Longest prefix match, or the hardware forwarding lookup. So this is complicated because you've got all these subnets floating around. You've got subnets that cover other subnets, and it's super dynamic. So again, this is where if it were free, I would just throw a giant TCAM at it and say I'm done with it, and it would be great. TCAMs to build TCAMs that are fast enough and big enough to do what these switches need to do, I simply can't afford to build the thing, and it's not close. So what I end up doing is I basically build this kind of hybrid hard combination of a bunch of digital logic that does some math, a bunch of TCAMs that do some part of the lookup, and then a bunch of SRAMs that do another part of the lookup. And so if you think of the fib as a big tree, which is exactly what it really is, right? Imagine taking the entire IPv6 address space and drawing it out as a tree, right? Every subnet just has childs, and maybe there's nothing below you in the tree, and maybe there are 150,000 things below you in the tree. You don't know until you build it. But you basically take that data structure and you try to map it into a hardware lookup engine that has some combination of TCAMs up at the top and some combination of SRAMs in the middle, and usually some combination of SRAMs and maybe HBM at the bottom to actually store the answer. And then if one of those lookup cores or engines or whatever you want to call them, if one of them's not enough, then you start stamping out multiple of them in parallel so that you can make your packet rate go. And at some point, you just got to decide that's a substantial amount of space on the chip. And it's like, well, I can do one more copy of the lookup engine and increase that packet rate by some number, but then something's got to go over the side of the boat, right? Because at some point, it's just not, I can't just add stuff, right? It's like, once you had 170 people on a 737, to get another person on, you got to throw somebody off. And hardware design is very much the same way.
So what you're implying here, right? You're just saying it, is that the memory design we end up with, that is the trade-off of costs and packaging and heat dissipation and so on, ends up impacting network performance depending on the operation I'm trying to do. Is that fair?
Yeah, that's fair. And there are chips where everything is kind of engineered to run at a fixed number. And this is kind of it's like it fits or I sits, right? Either the state that you're trying to store will fit in the machine you have and it will run at performance X. Great, super simple. But if it doesn't fit, then it won't run, right? I call that the cliff function. It's not a step function, it's a cliff. It either fits and your performance is X, or it doesn't fit and your performance is 0. Then you can also build machines that are way more fungible, where you say, okay, like the first example would be, well, I can't make it fit in structure A, so I can push the state into structure B, but it takes more memory accesses, so it's got to be slower. And the hardware has to be designed to be capable of that. The software has to understand it and program it differently. You have to explain to your customers that they might not always see exactly the same performance. And so there's a whole bunch of trade-offs that go with that design decision. And if you're writing code in C to run on an x86 machine, like your performance is going to have little wiggles all over it, right? Because you've got all these memory accesses and the compiler abstracts all of that from you, right? The compiler figures it out and tries to build cache lines and manage all that stuff. And it's like all the same work's getting done. It's just you can't really see or control any of it. When we're trying to do 10 billion packets a second, I got to know where every single memory access is. There's virtually no roll in your own memory access, right? It's like the programmer literally says, this key goes on this interface at this clock, and the answer will come back at n plus some number clocks. And the whole thing has to work that way. And if you can't make it fit, you can't implement the feature. And that's that's the thing that makes people crazy, justifiably so, when they buy these super expensive, super high performance systems, and then somebody tells them I can't do the feature. And it's like, for want of a nail, the war was lost, right? It's like, I just need one more memory access right here, but I don't have it. The memory doesn't exist, the interface doesn't exist, and this ain't software. I can't just create it. If it wasn't there when I built the hardware, it's never there.
Now, some of us network engineers are nerds who like to take the covers off of things and point at the chips on the board and go, ooh, if I'm looking up memory, am I going to see memory as separate chips, or do they tend to be packaged within a larger ASIC?
The SRAM you won't be able to see. The SRAM is lithograph from the exact same transistor library that all of the digital logic is. Now, if you get out a really good microscope and you know what you're looking for, you can actually see it. It has a different physical layout, or it has a what's the word I'm looking for? It has an identifiable physical layout. It's rows and columns. So if you get out a really good microscope, you could go, oh, that's an SRAM, and it's roughly this many bits wide and roughly this many rows tall. The HBMs come in separate discrete packages. They're, I don't know, I guess about a centimeter square. And they have to live very close to the edge of the main die, because those wires, those 1,000 little tiny wires that make up the bus, they can't be very long. Don't ask me exactly how long, but they got to be really short. And then regular DDR memory just comes on sticks, and we don't use that on anything high performance. Now the control plane uses it, right? If you see those big server memory DIMMs next to a chip on the board, that's going to be the control plane CPU and the memory that it uses. But all those SRAMs and TCAMs, now there were and still are what we call external TCAMs, which is sort of a misnomer. And And so there's
Yeah.
lots of products where, we would say, oh, well, we have the one that has the TCAM on it and the one that doesn't. It's not the greatest terminology, because even the thing that doesn't have the TCAM still has some TCAMs. It's just they're internal and they're smaller. But then you have this big external TCAM that lets you do more routes or more ACLs or more whatever. And like, in some ways, we're grossly underselling the work that went into that thing, because like that thing isn't just a bunch of TCAM. Like, it's not like it's just a bunch of memory that you stuff off to the side. What it really is a bunch of memory wrapped in a whole bunch of logic that lets you. It's people call it an external memory device. I've always called it a coprocessor. So like, instead of saying, like, what you do is you say, here's the key, just give me the answer. And it's not just storing all the state, but this thing is also managing all those lookups and, sometimes buffering, small numbers of things so you can get better performance. I mean, it is a really, really complex machine that sits over there. And people are always like, oh, why is it so much more expensive? It's like, well, two reasons. One, like that external TCAM is just as big as the main chip, sometimes even bigger. So like, it's like we draw it as this little box on the block diagram, but in reality, it's every bit as big as the thing that it's helping out. And you're getting hundreds of people to write a boatload of software to manage all that stuff too. And so that's where a lot of that cost comes from.
Well, okay. So let's wrap up this show, LJ, with a question in the Slack group that caused me to reach out on LinkedIn and connected you and I. This is a ton of background and incredible information to answer what is, in theory, a relatively simple question. So for those of you who are unaware, Packet Pushers has a community Slack group. You can join that at packetpushers.net/community. It's free. There's a few rules. Read them, jump in. There's thousands of other people in there already having network nerd conversations every day. Here's the question. On the latest episode of the IPv6 Buzz podcast, a separate podcast in the Packet Pushers Network, but on the latest episode of IPv6 Buzz, there's a suggestion that the number of longest prefix matches a TCAM can store is variable based on the distribution of prefix lengths in the set of prefix. Now, I always thought the number of prefixes a TCAM could store was finite. I remember watching closely 15 years ago as the IPv4 table grew, and we worried we'd hit the limit of our hardware. At the time, I thought the way we carved the TCAM gave us fixed limits, but is that incorrect? If we have 100,000/42 IPv6 prefixes, does that use less TCAM than 100,000/43 v6 prefixes?
So, a couple of things. A lot of times what people will call, quote, the TCAM is not really a TCAM, or certainly not just the TCAM. Almost every fib implementation that uses a TCAM is some combination of both the TCAM as like a memory and a very primitive lookup piece of hardware. It's also all that control logic that's wrapped around it. Doing LPM lookups with, because you have to manage inserts and removals and covering prefixes. It's a pretty complex beast. And so I guess the first order theoretical answer to the question is yes, it would use less TCAM to store a bunch of /42s than it would to store a bunch of /43s, but only if you built a TCAM to store 42s. So if I pick a perfectly generic TCAM where the kind of fundamental width is 80 bits, I can basically either use 80 or use 0. So if that's the thing that I'm building, if that's my building block, then a 42 and a 43 actually look exactly the same. Right. Now, what you end up with, and we talked a little bit about this, is like most high performance fib lookup engines are some combination of TCAMs and other memories. And what you basically end up doing is chopping up that IPv6 lookup space into, you can almost think of it as like layers. And so I got to make the numbers up. If your TCAM is 80 bits, then you could basically look up the first 80 bits of the address in the TCAM. And then now I've got another, do math. Now I've got another 48 bits, right, that I got to figure out some other way to get to. Well, if I've got a 48-bit TCAM laying around, perfect. Crap, I don't have a 48-bit TCAM laying around. So usually what you'll do is, because I don't want to store the fat part of the tree in TCAM just because it's too much state. So I build other tree or tree-like structures out of other memories that kind of let me fan out the bottom of the fib table. And so what you get into is, it's like, you can almost think of it as like a compression algorithm. Like if somebody says, hey, I'm going to give you a file and you're going to gzip it. How big is the file going to be when you finish? I'm like, I can't tell you because I don't know what's in the file yet. And if you say, oh, it's source code, I'm like, okay, it's going to compress really, really well. And they're like, oh, it's, a recording of Orange is the New Black. I'm like, that's not going to compress well at all. So the algorithms are optimized around rule sets or databases that we think at least we know something about. Like, we know we've got a pretty good idea what the global fib table looks like, right? That's been more or less similar for a while. But what we don't necessarily know is what any individual, single company's VRF table might look like, because they might choose some really unusual addressing plan, and then as the hardware designer, I got to eat that. Right, I've got to either know about it in advance and hopefully build enough flexibility into the algorithm that it can adapt to it, or I've got to have enough flexibility that I can get away with sometimes throwing more memory at the problem. And so, to that question, generally speaking, if you have lots of the same prefix lengths, that's good for hardware. We like that, right? Because I can compress the state out. Usually, if you have lots of prefixes blobbed together, that's good. Again, if you can visually think about the V6, and we use V6 just because it's easy. Like if I think about that number space and I say, I'm going to give you 500,000 routes, 500,000 prefixes from random prefixes and random masks, you have just broken every sensibly designed hardware lookup engine that's ever come up with. Now, what you have not broken is 500,000 entry TCAM, because the TCAM gobbles up variability for dinner. It doesn't care. I've got a bit for every single thing, right? Now, it's astronomically expensive and it will light your house on fire, but it's super, super well adapted for that particular thing, right? And so what you really end up doing is saying, I got to build something that's fast and reasonably affordable and won't burn the building down. So I've got this combination of different memories stacked up in different ways, and this is where I definitely wave the flag and say, this is super implementation dependent. And there are, like, you can literally go from one really fast switch to another, and /97s will work just fine, but /98s look really bad, right? And it just comes down to where did people draw the lines in when they design the architecture, or something like, well, it used to work really well for 97s, but then I needed to add one more bit so I could have more VPNs. And that one more bit now means that those 96s look like 97s to the hardware, because the hardware is kind of dumb and doesn't care. And so, imagine that you've got, 100 million of these little micro optimizations kicking around in the hardware design. And now you've got some idea what I do all day.
Well, what you're telling me is it depends. That is, depending on my specific situation and what I'm trying to accomplish from a network engineering perspective, one hardware platform might be better for me than another, and I actually need to understand chip and memory internals fairly deeply if my needs are that specific.
Yeah, it's gonna help. And the other unpleasant reality is that in order to go faster, which usually also implies cheaper, the only way to do it now is to have more parallel memory, because the memory itself isn't getting that much faster, right? Like the memory that I have in 2025 to design a 50 terabit chip is not 10 times faster than when I was designing a 5 terabit chip. It's not even close to 10 times faster. Like, it might be 30 or 40% faster. And like I'm trying to stack like binary orders of magnitude improvements in performance and bandwidth using tools that are getting 10 or 20% better at a chop. And so the
Mhm.
only way to do it is more parallelism, better algorithms, in a lot of cases doing less, right? Like just the sheer number of features that I can do on a 50T chip is way smaller than what I can do on a 1T chip. It's some because it's the same number of memory accesses, right? If I like to do this super complex feature path that the old thing I'm trying to replace, the Cisco 1, 2, 3, 4, 5 would do this. Why does the 5, 6, 7, 8 not do this? It's like, well, because the 5, 6, 7, 8 is way faster and way cheaper per bit and way lower power per bit, and in large part that's what moves routers.
So is there a way for people like buying these devices? Is there sort of like a, I guess, rule of thumb for like, if I have this use case, I should be thinking about this kind of memory. If I have that use case, I should be thinking about that kind of memory, or this design, whatever.
Design the memory part, yes, but you can really only do it indirectly, right? Because at some point you're relying on me and my happy band of actual hardware engineers to sort of figure out what the right trade-offs are, right? Where do we add memory? Do we add more parallel memory? That sort of stuff. I do think it's super helpful to the extent that you can scope whatever you think it will be, and this gets into kind of, I always joke that layers 8, 9, and 10 of the OSI model are politics, religion, and economics, and this is definitely into that category. You can spend more money and use more power and take up more space on a system that is more flexible, and that gives you some amount of space to grow into. Or you can buy something that covers what you need now and then not grow. And those are kind of, they're at least the ends of the continuum for making that choice. I think there's real value in folks understanding just kind of what the highest level trade-offs are, right? Because if somebody comes to me and says, "Oh, I'm thinking about buying a purple switch or a green switch, which one should I buy?" I'm like, "Well, what are you trying to do?" And one of those dimensions is going to be the green thing does what it does today, and it's never really going to do anything else. And the purple thing does what it does today and will be able to grow in these particular dimensions. And hopefully I can give you somebody can give you some idea of what those dimensions are. And then sort of figuring out, what is a reasonable expectation for how long is this switch going to live in the network, and is the stuff going to change, and are these forwarding tables going to get way bigger, and if so, what am I going to do about it? And so there's a bunch of those kind of questions, and ultimately it's just about trade-offs, but they're not always simple and they're not always obvious. And what I try to tell customers is like, I am not here to tell you how to run your network, but I am here to tell you what it's going to cost. Right. And if somebody say, it's like United's like, look, we're not telling you which seat you have to buy. We're just telling you here's the prices. And so like having I hope folks have at least a slightly better understanding of like, why are these things designed the way they are? Right. The answer, there's always actually an answer. And at least half the time it's not that we're just stupid. Maybe half it is. I don't know.
I have so much more appreciation for what is happening inside these boxes right now, based on the cover you've pulled off. Like this is complicated stuff.
Yeah, it is. It is, and part of the reason it's super fun is it's like if you need something to switch a couple of gigabits inside your house, you can do that, right? It's not that expensive. It's not that hard. You can go buy, well, not you, but people who build these things from OEMs can go buy a $4 4-port GigE switch and a $15 ARM CPU and write a bunch of code, and it'll work. And it's hard code because routing is fiendishly complex. But you can do it, and you just a lot of those trade-offs are made for you, right? Which is the chip does this, it has this many things, tough. Whereas from like the fun part about where I sit is there's an awful lot of stuff the chip can do, but I'm never going to be able to expose all of it to a customer because I can't do it all at the same time. Right. It's like I can either implement feature A or I can implement feature B. Right. I can either save Rose or I can save Jack, but somebody's going to the bottom of the Atlantic. And so it ends up like the product, kind of the product management side of it is basically choosing, do I want to do feature A or do I want to do feature B? and that's repeated again and again and again and again. And then, if you want, you can have different platforms for different market segments, and you get into the whole product management rabbit hole. But that's kind of what we do for a living, is try to figure out what are the right trade-offs to make. And if people can ask, what's the exchange rate for X, right? I want 17 million entries in the FIB. What's that going to cost? Not necessarily dollars, but what does that mean I can't do? And the underlying memories end up being a pretty big part of, at least in the scale dimension and the performance dimension, of what you're actually capable of.
LJ, there may not be a good answer to this question, but I want to ask it anyway. So a lot of engineers are faced with the task of needing to carve up their TCAM resources in some way or another. Is there a such thing as rule of thumb or best practices that can guide them?
There's really not. I think the biggest challenge is there, from the OEM system designer side. We have some memory. To some extent, we can carve it up. We can make it flexible. Again, some we can make really flexible, some we can't. We kind of have to pick something. That's usually mostly a function of what market segment we're trying to sell into, right? This is the dumbest terminology that I hated since 1997, and I still hate now. It's if it's a switch, I'm going to carve some more L2 stuff, and if it's a router, I'm going to carve more L3 stuff. That distinction in 2025 is kind of bunkus, but it's really, really hard because the average network is the average of a bunch of things that don't actually look like that. And so when you've got systems that have that kind of flexibility, sadly, a lot of people don't know that flexibility exists until they run out of something, which sucks and it's painful. And we could do a whole podcast on great war stories of when you run hardware forwarding implementations out of a resource. And so I wish I had, I wish I had a better answer, because it's if you're in a spot where you have to make that decision, you've probably already run out of something. And for somewhat justifiable and somewhat hand wavy, I'm really sorry and an apologist reasons, the software complexity on the back end to implement that kind of flexibility and carvability is really hard. I know it looks like it looks simple. It is really hard, because if you get it wrong, the thing is a doorstop. And it turns out people get really, really mad when you turn their switches into doorstops.
Those are expensive doorstops. Oh, LJ, 90 minutes in, absolutely fantastic conversation, educational, enlightening, in some ways just giving us a peek, because to talk about it thoroughly sounds like you'd need several years of lecture to be able to get through all the material. Thanks for spending time with us. This was really great. Now, I'm going to guess our community's got questions for you, perhaps. Sure. And if they do, can they reach out to you, and how do they do that?
Absolutely. Yeah. Do it on the Slack. That way everybody can see the question and everybody can see the answer. I'm on LinkedIn, and I'm L. Wobker at Cisco, and have been since 1997. Turns out when you have a really unique last name, you're pretty easy to find. And yeah, but I think the Slack channel is probably the right place. Just tag me in there, and I'll try to get to it as I have time. And to me, the idea is the more people understand kind of how this stuff is actually built, it's easier for them. It's easier for us. People make less bad, really hard decisions. They're not going to be easy. We're living in resource constrained environments, and that's always painful. But at least having a better idea of what the exchange rates are can hopefully help folks, figure out how to ask the right questions to whoever they're talking to, and kind of understand why these things work the way they work.
LJ, just a heads up, when this episode comes out, you might want to allocate a little bit more personal memory to answering questions on the Slack. Do you have any bits free?
I'll get right on it. I'll try to find something that's a reasonable latency too. I'll try to find some for sure.
LJ, thanks again for coming on Heavy Networking today. And again, if you're looking for LJ, you can find him on LinkedIn. That's LJ Wobker. We'll have a link for that in the on packetpushers.net, where you'll find the show notes for this and every show that we publish on Heavy Networking. We also got a link to a YouTube that was published with LJ speaking, I believe, at a Tech Field Day event on the Cisco 8000 series, Under the Hood, way back from 2020, with lots of good information in there as well, if these sorts of switch internals really get you excited. Thank you for listening to Heavy Networking today. This was, again, putting the heavy in heavy networking are episodes like this, and LJ really brought it. And we do these hardware shows from time to time because how a box is designed can make a difference in a buying decision, which I hope is abundantly evident to you now as after you've listened to this show. So, I mean, maybe you don't want this specific box because it can't perform this feature you need at line rate, and you really need to do it at line rate. And so maybe you want this other box instead. Well, knowing that all these things are things can make sure that you are researching the right things and asking your account reps the right questions. Okay, go get some merch. Store.packetpushers.net. Join our Slack community that we've been talking about. Sub to our 2 free and excellent newsletters, Human Infrastructure and Packet Capture. Follow us on YouTube, like, comment, and subscribe everywhere you listen to Heavy Networking. We would really appreciate you doing all those things. And from Drew and me, have a fantastic week. You are a most excellent human in a world that needs all the excellent that we can give it. Last but not least, remember that too much networking would never be enough.